As we continue to talk about applied statistics, let's take a look at what I call the data menagerie, or sort of a zoo, if you will. Oh, that's not the tool I wanted. I want the pen here. A zoo of data. So sometimes you'll see these called other things. There are many terms that we could use for this, and so sometimes you'll see instead of the word levels, you'll see maybe the scales of data, or type. What type of data do we have? And then sometimes instead of the word data, we see the word measures. And of course, measures and data, we measure something to get data, or measurement. Sometimes we'll see the word measurement in place of the word data. So let's take a look at some of the different levels of data. But why do we need to do this? Well, the main reason is that different data require different statistics. So if we have a different type, the type of data that we have is going to determine what type of statistics we can appropriately use on that data. And again, our goal is to make justifiable claims using the data. Well, in order to make these justifiable claims, we need to use appropriate statistics for our data type. So here is one way to classify our data. It's sort of a hierarchy that we can take a look at. And of course, we're going to go from less order, in this case, to more order on this side. And that's not necessarily a good or a bad thing. It's just an indication of what we've got. So over here on the nominal side, this is the least order side, we have nominal data. And this is, we could sometimes call this categorical data, where we just have a set of labels or categories. And so it's right there, the word nom, name. In this case, we're naming things. And so a good example of this would be sex, job title. And these are things that, if you look at the set of the sexes, we've got male and female. These are the biological sexes. And there's not really any ordering between these things. If you think about it, if you wanted to sort, you could sort them alphabetically, but in this case, you're not really sorting them any meaningful way. Same thing with job title. You might have CEO, you might have CFO, you might have janitor, just to go to both sides of the scale. And even there's really no inherent sorting of these things necessarily. They're just titles or labels. You might have position on a sports team, or role in a surgery suite, for instance. These are all nominal types of data, meaning that they don't necessarily have an ordering. So to add a little bit of order, we go into the ordinal data, and this just means that we can, I like to think of it as we can sort this data. We can sort ordinal data. There's a sequence between the different data elements. So if we had, a scale from 1 to 5, something like this, we see this kind of thing all the time, like least satisfied to most satisfied, or strongly agree, disagree, all these sorts of scales. That's ordinal data, and that there is a relationship. If we see a 5, we know that the 5 is greater than the 1. If we see agree, we know that the agree is greater than the strongly disagree. So there's an ordering now in this set of data. So that's the idea behind ordinal data. All we've done is add an ordering, but we don't necessarily know the interval between agree and strongly disagree. How much is that? How much agreement do we need to go from neutral to agree? And is that the same amount of agreement that we need to go from strongly agree, or from agree to strongly agree? We don't know what that interval is. And so the next type of data is exactly that, the interval data, where we have a nice evenly distributed scale. So not only do we have, we've got the two bounds, but we also know that the data in between are all the same distance apart. So this would be, a good example of this would be years. This is the example that our text uses. Sometimes you'll see things like Fahrenheit or centigrade, Celsius type temperatures also fit into this category. Let's see, we could do, I think those are probably some of the better examples. So in this case, we've got data where the intervals are defined, like each Fahrenheit degree is the same amount. So if I go from 101 degrees to 102 degrees, that's the same amount of increase in temperature as 201 degrees to 202 degrees in either centigrade or Fahrenheit, but the number 0 degrees in either one of those isn't necessarily a highly meaningful thing. It's not a true zero per se. It's just an arbitrary label that we put at somewhere on the scale. We said, well, this is going to be 0 degrees, right? We're not looking for some true minimum, and that's why we have things like negative 2 degrees Fahrenheit. Now, if we take the 0 point and we actually make that a meaningful thing, meaning that it's got a real meaning. It's not just an arbitrary label that we picked for some point on the scale. For instance, again, centigrade, 0 degrees centigrade just happens to be the temperature that water freezes at. We picked that as the arbitrary place that we put the label. Well, degrees Kelvin actually begins at absolute 0, right? So that begins over here at our true 0. So degrees Kelvin actually is a ratio scale, meaning that 0 in this case is meaningful. And other examples of that would be things like weight and height. Whereas if we had true 0 degree or 0 inches of height, that would mean if our height was in fact 0 in some unit, then we would know that we have no height. It's a meaningful 0. Same thing with weight. If we weighed 0 pounds, or our weight was 0, then we would know that, well, we wouldn't exist in that case, right? But there's a true 0. So this is in a ratio scale, we have the interval, but then we also have a true 0. So these are the different types of scales. And as you can see, we're adding more and more order as we go along. The ratio scale, we can still sort these numbers by value. They have real value, and we have that real 0. Interval scale, again, we've got order, but we just have predefined intervals. And then the ordinal scale, we don't necessarily have predefined intervals. All we have is the ordering capability. And a nominal, we don't even have the ability to order things. We just have some labels. And now all of these are useful. We've come up with useful types of data for each one of these. But they do affect the types of statistics that we can do on that data. Some other data concepts, we've got discrete versus continuous. So discrete data means that we have discrete values. So the example that our text gives is number of visits. And the number of visits can only be discrete values, 0, 1, 2, etc. Whereas a continuous variable would be something like temperature, meaning that there are an infinite number of possible temperatures. We could be 1.01, 1.001, 1.0001, and we could continue doing this almost forever. Now, whether we could actually measure those or not is kind of beside the point, but the idea is that there is an infinite number of possible temperatures, whereas there's not necessarily an infinite number of possible visits in between each discrete number of visits. So we've got separate or distinct values, whereas in a continuous variable we have infinity, both in the large and in the small, is one way to look at that. So then we've got numeric versus categorical data. Obviously numeric data is going to be numbers, and categorical data typically is more like data groups. So we could have age group. Now we can convert from one to the other, right? Age itself is a numeric variable, but we can convert it. Now, by the way, is age discrete or continuous? That's a good question, right? Age, of course, would be a continuous. There's an infinite number of possible ages that we can have. Now, if we assign it a unit like year, and we could potentially make it discrete if we wanted to, and we could even go further and make it an age group by saying, let's say, we define some cutoff ages, and we've got, child, then we've got youth, and then we've got adult, and maybe way out on the end we have senior. Let's say someone who's 100 years or older. We could say, that's a senior. So we've got these different types of groups that we could potentially put them into. So we can convert a numerical variable to a categorical variable. quantitative versus qualitative data. And we've spoken about this to some degree in the past, but quantitative data is going to be, in this case, we're going to use some of the language that we've already got. This is interval or ratio data. And we're going to define qualitative data in this case is mostly categorical or just free text in some cases. So this could be nominal or ordinal data. We can still have ordinal qualitative data, but it's not necessarily going to be quantitative, meaning we have a difficult time quantifying that data. That's the key word there. And then metric and non-metric sort of kind of fall into the same categories as quantitative and qualitative, at least the way that our text uses it. Metric data is going to be, again, either that interval or ratio data, whereas non-metric data is going to be our nominal and ordinal data. And with all those terms in mind, we're ready to kind of look at the key differentiator. The key differentiator that we're going to use in this case is the parametric versus non-parametric data. So parametric data, we have that continuous data, interval data, ratio data, and in this case we're going to assume in most cases that the distribution is normal, and for that we can use a certain class of statistics. And this is data that there's some sort of scale, there's a value, and then we've got some sort of bell curve, which I have a great difficulty in drawing, but we've got this bell curve around some midpoint, central tendency we call that, and that's what we're going to look at. And non-parametric data, rather than doing that, it's more like we've just got some buckets of whatever types they are. So even if we order them, and there'd really not be any meaning to the order here, but if we had male and female, for instance, there's no reason that we couldn't swap those. And of course, if we swap them, then our distribution would be different, right? We would be reversing the distribution. And so that's, and if we had a category that had more categories, other maybe, let's say there was, some sort of animal that had 3 possible sexes. Well, in this case, we would have, again, a third category, but the ordering of these categories is not necessarily critical. Now, of course, we can also look at ordinal data as being non-parametric. So that's something to keep in mind. But we've got parametric and our non-parametric statistics, and these are the difference, or these are the two classes of things that we can use, and this is the way that we need to differentiate as to what we can use.